So we're looking at functions now and what it means to be a function, looking at an equation and telling if it's a function or not, or looking at a graph and telling if it's a function or not. So in our textbook, we're starting chapter 3. And so first, let's talk about what a relation is. So a relation is a correspondence between two sets. And so the first set are usually x values. Sometimes we use different variables. So x is the set of values in the domain. And y is the set of values in the range. So we can think of this, there's some correspondence between these x values that we're going to put in here and our y values in here. And so that correspondence or a relationship is that equation normally that we're using to map values over. Okay. Another way we can think about this, our x values, we also think of as our input. We put that value in for x, and we simplify that expression down using our rules and operations of arithmetic, and then we get an output. So we think of x as an independent variable, and our output is dependent on what we put in for x. So y is normally our dependent variable. So these are all kind of things that mean the same thing. And so sometimes we will see that relation written as a point, xy. So let's look at some examples real quick, and then we'll get into what it means to be a function. Those are special relations. Okay, so in the following problems is a relation expressed verbally, and it's given the following. So, and once we read this verbal meaning, we want to determine what the domain and what the range of the relation is. So it says the density of gas under constant pressure depends on temperature. Holding pressure constant at 14.5 pounds per square inches, the chemist measures the density of the oxygen sample at temperatures of 22, 40, 70, and 100 degrees Celsius, and obtained the densities of the following: 1.411, 1.305, 1.229, 1.121, and 1.031 kilograms per meter cubed, respectively. Okay, so again, a lot of information in there, but let's go and we're looking at what they're asking. So we're trying to determine the domain and range of the relation. Okay, so the density of the gas is a constant pressure, depends on temperature. So the density depends on temperature. So a holding pressure at a constant 14.5 pounds per square inches, the chemist measures the density of the oxygen sample at certain temperatures. And so looking at this, it says density depends on temperature. So I know that my temperature is my input. And my density, since it depends on this is my output. And so maybe I should do temperature here. And density here. So it says the following. If I have a temperature at 0.22, sorry, I don't think that's 0.22. I think there's a comma in there, I just can't see. So we have a temperature of 0. I'm going to just do this vertically down. 22, 40, 70, and 100 degrees. And these are all in Celsius. And the densities that have occurred is 1.411, 1.305, 1.229, 1.121, and 1.031. And it said respectively, and this is kilograms per meter cubed. So temperature, this is our domain. And the density at that temperature is given by whatever formula. So once we put in that temperature, this is the density we would get back. And that is our range. So that was actually part B. Part A says express this relation using a mapping and express the relation as a set of points. So there's a couple different ways that we can do this. And so let's just write this out. So our domain in this case, we have 0 degrees, 22 degrees, 40 degrees, 70 degrees, and 100 degrees. And then we have our range. And so our outputs we get back. So the 1.411, 1.305, 1.229, 1.121 and 1.031. Okay, so that's our domain and the range in that set. If it asks for the mapping, basically how I set it up, this problem in general, it's easy to see the mapping. So basically, you're just kind of mapping what 0 degrees gave us what back. It was 1.411 kilograms per meter cubed. The 22 degrees, so basically just draw an arrow. So that would be what part B would be saying. And part C says express the relation as an ordered set of points. So basically, another way here that we can express these are points, and that's usually how we see them. And so our point, and I'm just going to do a couple of them. So X value is 0 degrees, our Y value we got back is 1.411. So 22, and I wouldn't actually put the degrees in there, I wouldn't put my units. 22, 1.305. Okay. So functions. Are relations where every input, which is the value in the domain, corresponds to exactly one output. A value in the range. Okay, so for every X value, there's only one Y value that corresponds to it. That X value has to be in the domain of our set, though. If it wasn't in our domain of our set, that wouldn't make sense. And so looking at the following example, we're going to determine the domain, the range, and then determine is this relation a function or not. So let's say you're given the following. The level of education, and is one set, and the average income is another set. And so the first set says less than 9th grade. And there's an arrow from there. And the average income, if the person was less than 9th grade, was $18,120. So if the person was 9th grade through 12th grade education, the average income was $23,000. $251. High school graduate was $36,055. Some college is $45,810. And college graduate. Which is $67,165. Okay, so find the domain, find the range of each of the relation, then determine whether the relation represents a function. So which one represents domain and which one represents the range? So we kind of have multiple sets. And so for our first set, let's look at less than 9th grade. Well, less than 9th grade that could be kindergarten. I guess we could have pre-K in there. Pre-K, K, first, second, third, right? Fourth, fifth, sixth, seventh, eighth, 9th through 12th grade. So 9, 10, 11, 12. Some college, usually don't call it 13. I don't know, what do you want to call it? Freshman, sophomore, junior, senior. Oops. Messy. And then you have your graduate work. So working on masters or whatever. Okay. But we kind of get the idea. And then our range. This is our income, average income. So we get back our set, the 18,120. And then we have the $23,251, the $36,055. So all of those different amounts. Is there a question? I don't know. So I don't have the question thing up. And so looking at this, what is this relation, a function? Okay, so again, in order to be a function, for every input you put in, every value in our domain would only give us back one corresponding output. So if you were, let's say, only got through pre-K, what income would they get back, or average income would they get back? Well, that would fall in this set, right? And they would get back the $18,120. Same thing with everybody here, pre-K through 8th. But if I choose one of these inputs to put in, am I getting back multiple incomes in here? You know, in that one set, I'm only getting back one income, that average income of 18,120. So for every input I choose, there's only one corresponding output for that. And so this is actually yes. This is a function. And so I just kind of wanted you to know it is okay for different inputs, or different values in the domain, gives you back the same output. Value in the range. So there's multiple inputs in our level of education that would give us the same average income. But every input we chose only spit out one output that was available. So it's a function. So just to be by terminology, there's equations, can be written in different forms, right? And so last week we looked at equations of lines. One was written in slope-intercept form, one was like point slope formula, or one was in standard form, but they were all equations of lines. And so just kind of terminology, we say that an equation is in implicit form. And usually we don't talk about this until calculus. Maybe that's in the next section. I'll get back to that. Oh, wait, there it is. Implicit form. I couldn't think of the other word. Explicit form. Okay, so implicit form is when you have variables on both sides of your equation. So the variables are on the same side of the equation. So for instance, ax plus by equals c. 2x plus 3y equals 6. Or last week we were working with circles. X squared plus y squared equals 1. And so this would be an implicit form of an equation. An explicit form, a lot of times we work with, is where it's in the form of y equals, or your function is equal to. So maybe, so y is equal to, or f of x is equal to. So maybe f of x is equal to x squared plus 3x plus 6. It's just another way of writing y. This would be an explicit form. So determine the following. If the equation defines y as a function of x. So if you're looking at an equation, it's actually better if we can rewrite it, and if it's not given to us in that form, if we can rewrite that equation in explicit form. So when it asks you to determine if an equation is a function or not, and it's not written in explicit form, you want to put it in explicit form, and that's easier than to tell a lot of times if that is a function or not. Some of you might be able to recognize what the equation is and if it's a function or not by like the graph. So first thing that you want to do put the equation in explicit form. A lot of times from there, we can tell if it's going to be a function or not, but if you can't tell, if the equation is a function, an explicit form, try plugging in different numbers for x. So in order to see if it's a function, we're basically testing every value we plug in for x. Are we only getting back a single y value if that x is in the domain? If you can plug in one value in for x and you notice you get more than one x value or y value back, then it's not a function. And so if you could just show one example, or you can see that, then you can say it's a function or not. So let's look at the following. And so determine if the following is a function or not. So what if we had y is equal to x squared? Okay, so it's already in explicit form because it's already in the form y equals. And so think to yourself, if you plug in a value for x, are you going to get one y value or multiple y values? So if you plug in 0 for x, you get 0 squared is your y value, which is 0. So there's one x value corresponds to one y value. If you plug in 1 for x, 1 squared is 1. So this one x value gives me one y value. If I plug in -1 for x, so square it, you have to carry the sign. -1 times -1 is +1. It's okay, I get the same y value back from different x values. I'm just seeing that I'm only getting one x value for every only getting one y value for every x value I plug in. And so I can tell right away that this is a function. So if you had x equals y squared, so this is actually not in the form and we want to solve for it. It's not in the form where y is by itself. Other equation, y was already by itself. And so we want to put this in explicit form. And so we can get rid of that square. We can use our square root factor. And so if we take the square root of both sides, we get y is equal to plus or minus the square root of x. And so right there, because of that plus or minus feature in front of the square root, I can tell there's going to be an infinite number of values I can plug in for x, and I'll get two separate y values. So for instance, if I plug in 1 here, I get y is equal to the positive of square root of 1, which is 1. But also, I get back, if I plugged in 1, back -1. So one x value gives us more than one y value. So this equation is not a function. So looking at another equation, so let's say we had x minus 1 quantity squared, and then in parentheses we have y plus 1 quantity squared is equal to 4. So would this give us a function? Well, hopefully you know what this shape is. So this is a circle, right? We saw that the center is in the form that we could tell what the center is. The opposite sign for the x is our x value of the center. So this would be 1, -1. And our radius, this is r squared. So it would be square root of 4, which is 2. If I graph this, at 1, -1. My center, and we talked about we could graph this by going up, down, left, and right from how much our radius is from our center. Oops, it's not 1, right? It was 2. And I did it right in the first one. Okay, it's supposed to look like a circle. So if there's a value of x that would give us multiple y values on our graph, then it's not a function. So if we can show at least one. So here's a value of x. So if I look on my graph, here's a point on my graph, and here's a point. So these are points that satisfy my equation. If I plug them back in here, I get a true statement. And so this is not a function. So I was kind of showing it a different way where we could have solved this for y. If you hadn't seen that or explain it that way, we could isolate our square root or our quantity square. So this is the same thing as 4 minus x minus 1 quantity square. Get y by itself, you'd have to take the square root of both sides. If you take the square root of both sides, you have to put that plus and minus in front of 1. So we get y plus 1 equals plus or minus the square root of this whole thing. And right here, that plus or minus, that tells me I'm going to get 2 separate y values back. For every x I plug in. Or most values of x. So that actually brings us to a rule. So notice if I draw a vertical line through those 2 points that I had found at x equals 2, if you can look at a graph and you can draw a vertical line through that graph and that vertical line intersects the graph more than once, then it is not a function. And that is called the vertical line test. So vertical line test can be used to test for function, to see if a graph is a function. So if you can draw a vertical line anywhere on the graph and it intersects a place more than once, then it is not a function. Okay, so if they ask you to find the domain, just do this. Domain again is all the x values that you can use. And so if you're given an equation and they're asking you to find the domain, it's actually best or easier if you work backwards. So if they're asking me to the domain of a function, I'm looking to see, am I going to have any troubles? Is there any value I could plug into this equation that would make it undefined? And so, or not give me back a real number, give me back an imaginary number, I. So if there's any number that could give you back I, so that would be a negative underneath a square root or an even powered root, or I can't divide by 0. If there's a variable that would make my denominator 0, then they can't be part of my domain, but anything else would work. And so looking at an equation and finding the domain. And determining the domain. You're going to look for trouble spots. So these are values that set the denominator equals 0. Values which give you a negative underneath an even power radical. Or I'm just going to say an imaginary number. And then the other problem spot, which we haven't talked about, and we really haven't looked too much about this, is logarithms. So logarithms, and we'll talk about logs later in the class, but it should be kind of a review. Logarithms, you can only take logs of a positive number or positive value. And so if you had a log or a value of x which gave you a log of a negative number, we'd have to exclude it. And so look for your trouble spots and then exclude your trouble spots from the domain. So the domain are all values except the trouble spots. So if you are given f of x is equal to a rational function x plus 1 all over 2x squared plus 8. And it asks you to find the domain of f of x. Okay, since this is a rational function, and that means I have a variable in the denominator, that's where I might have problems. And so I am concerned my trouble spots is going to be when my denominator equals 0. So I have to determine, is there any value of x, real number, that if I plugged it back in here, that I would give you back 0 in the denominator. And so I can solve for x here. So if I subtract 8 on both sides of my equation, I mean, there's multiple ways I can do this. I'm going to use the square root method because I have a perfect square in here. I'm going to divide both sides by 2. So we get x squared is equal to negative 8 divided by 2 is negative 4. I can use my square root method now. Take the square root of both sides. I get x is equal to plus or minus the square root of negative 4 plus or minus 2i. But this is not a real number. The domain, the set, our domain is a set of real numbers. So this is not a real number. So there's no real numbers. We need to exclude from the domain. And so that tells me that if I don't need to exclude anything from the domain, my set of x, that would mean that my domain is all real numbers. And so just look and see how they want you to express that. But I would normally express it in interval notation. We went over that last week. So that would be from negative infinity to infinity. So if we're looking at f of x is equal to x plus 4 all over x cubed minus 4x. So again, find the domain of f of x. So again, first look at where you may have troubles. A rational equation, variables in the denominator. So we can't have x cubed minus 4x. We are going to have problems if this is equal to 0. So last week, most of the week was working through different ways or different equations, solving different equations and different methods. And so here, notice we can factor this. We can factor out an x. We do that, we get x squared minus 4 equals 0. I notice that inside my parentheses, difference of squares, I can factor this further. So I have x times x minus 2, x plus 2. Set each factor equal to 0. So this is when x is equal to 0. This is when x is equal to, well, x minus 2 is 0 when x is 2. And x plus 2 is 0 when x is negative 2. Okay, so those, we cannot have x equal to these. So technically, any number other than those 3 numbers would be a solution to our equation. And so we can think of this as any number that is less than that -2, anything in between that -2 and 0, anything between 0 and 2, and anything bigger than 2. And so we denoted it with parentheses that we weren't including it. You might see it with open circles there if we were graphing it, but the parentheses makes more sense when we're looking at writing this in an interval notation. So we have multiple ways or multiple sets that we have to include. So we're looking from -infinity all the way to -2, parentheses. That union symbol means it's this set plus the following. So -2 to 0. Those are parentheses. Union 0 to 2, parentheses. Union parentheses 2, comma, infinity. So what if it was h of x is equal to the square root of 3x minus 1 all over x squared minus x minus 6. So we want to find the domain of h of x. Okay, so here we got multiple places that are going to give us problems that would not give us back a real number. So trouble spots. When you have 3x minus 1 is less than 0. And when our denominator, x squared minus x minus 6, is equal to 0. So if we solve this, so we have 3x minus 1 cannot be less than 0. So solve it. It's a linear inequality. So if we add 1 to both sides, we get 3x is less than 1. Divide both sides by 3. X is less than 1/3. And then this can be factored. So there's two numbers that multiply to give you -6 and add to give you a -1, -3 and +2. So x equals to 3 and x is -2. So technically, if x can't be less than 1/3, that tells me x has to be greater than or equal to 1/3 in that piece. And I know that x can't be 3 and x can't be -2. So all three of these things have to hold And so if we look at this, and sometimes graphing the solution is helpful, if I look at where 1/3 is, it's an important piece, -2, you don't have to really be accurate, and +3. So I know that x has to be greater than 1/3, but it can't be 3. Maybe put an open circle on these now. And it can't be -2. But I have to shade to the right of 1/3. Can't hit 3, but I can go past 3. So one of those numbers, that -2, isn't even part of the set from 1/3, greater than 1/3. It's what they share in common. And so this would be starting at 1/3, but not including, so parentheses, all the way to 3, but not including, so parentheses, union, parentheses 3 to infinity. Okay, so you should be okay with this notation, h of x, f of x, g of x. You should be able to work with that notation. So if you saw h of 2, for instance, okay, just want to make sure 2 was in that domain before I say let's find h of 2. So let's look at that equation again and just go over some examples. So if it said find h of 2, h of x is equal to square root of 3x minus 1 all over this x squared minus x minus 6. So basically, this is telling me to do is go in wherever I see an x in my equation, we're going to replace that with a 2. And so, because I like to do different colors, I'm going to go in and I'm going to put in a parentheses wherever I see an x. And actually, then I started realizing that's actually really helpful for students. So let's just go into that equation and put in a parentheses wherever you see an x in that equation. So h of 2, this is equal to the square root. We have a 3, you see an x, so put parentheses, and then a minus 1. All over, you see an x there, so we're going to put a parentheses, but that x is squared, so that parentheses is squared. Minus, you see an x there, put a parentheses, and then we have a minus 6. So now go in and wherever you see an x, we're going to replace that with 2. Before I do that, I'm going to see if I can save this for later. But maybe not. Okay, I thought maybe I could save some time. Okay, so plug a 2 in. Use your order of operations. So treat what's underneath the radical, which is called the radicand. Treat that as parentheses. So order of operations underneath the radical. Exponents come, no, there's no exponents. Multiplication come first. So we have the square root of 3 times 2, which is 6. And then we're going to subtract 1. Denominator, that's like a parentheses around that whole thing. Order of operation, exponents first. So we get 4 minus 2 minus 6. So this is the square root of 5 all over 4 minus 2 minus 6. 4 minus 2 is 2, 2 minus 6 is negative 4. So h of 2 gives us root 5 over negative 4. If it said find h of, let's say, 2 times b. So it's the exact same thing, except now instead of putting in some number, I'm putting in the whole expression 2b wherever I see an x. And so we're going to go back to our equation h of x, and we're going to rewrite it. And wherever we see an x, we're going to just put parentheses first. So we have square root 3, you see an x, put a parentheses. Big enough to put 2b in there. Minus 1, all over, you see an x, put parentheses. That is squared, minus, you see an x, put parentheses, minus 6. Go put 2b in wherever you see a parentheses. So this case, we're not going to be able to get a number, but we'll have an expression. We can simplify it down as far as possible. And so we have the square root of 3 times 2b. Well, 3 times 2, so that's 6b, minus 1, all over, oh shoot, accident. I accidentally pushed my off button. Come on. Okay, sorry. I don't know what happens when that happens. I accidentally turned off my tablet while writing, and then so I don't know what happens, what you guys see if it just goes black. And I hope that you guys are still there. It looks like it. Okay, so 2b quantity squared, 2b times 2b is 4b squared, minus 2b minus 6. There's nothing else I can do to simplify down this expression. And so we're done. So if it said plug in, so h of a plus h quantity squared. I'm sorry, just a plus h. So there's no number here, there's an expression. And so instead of plugging in a number, and it's more than one term, we need to go in and we need to plug in this whole value, a plus h, wherever we see an x in our equation. Again, I think it's helpful if you just go through and put in a parentheses wherever you see x first, and then go back in and plug in what they want you to plug in. So we have a 3, there's an x after the 3, so put parentheses, minus 1, all over, you see x, so put parentheses, quantity squared, minus, you see an x, put parentheses, and then minus 6. So go in and put a plus h inside your parentheses. And so Again, we can't get this down to a number, but we can simplify it. And so I notice I can distribute my 3 inside the parentheses a plus h. That would give us 3a plus 3h minus 1, all that underneath the radical. I notice I can distribute out a plus h times a plus h. I also notice that negative could be distributed to each term. So this is minus a minus h minus 6. Numerator, I can't simplify anything, so still my radical. I can distribute and hopefully, but I know I can't, looking at it, add any like terms. So if I distribute this out, I get a squared. This is an AH plus an AH, so plus 2AH plus H squared minus A minus H minus 6. And none of those are like terms in the denominator. Nothing simplifies. So technically, this form right here actually looks kind of nicer to me. Okay, so that brings us to a huge thing that you guys are going to be doing a lot once you get into calculus, which is called the difference quotient. A little later this week, we'll talk about the difference quotient because we're going to go back and talk about rates of change, which are basically kind of like slopes, the change in your y value over the change in your x value. The difference quotient is the following: f of x plus h minus f of x all over h. Okay, so the difference quotient is part of the definition of what a derivative is, which is one of the main concepts you're looking at in calculus. And so you really need to be able to get this down. So basically, nitpick it. You're going to look at different values. You're going to look at what is f of x plus h. This minus f of x, basically all that's telling us to do is distribute a negative to any term inside of the equation f of x. And then it's telling us to put this all over h. So, for instance, if you were given f of x is equal to 3x plus 4. And we want to find the difference quotient. So first, if it helps you, again, do it in little pieces. And so if we wanted to look at f of x plus h, we're going to go in and wherever we see an x, we're going to replace that with x plus h. And so first rewrite it 3. Let's put a parentheses wherever we see the x plus 4. So this is telling me take x plus h. And plug it in wherever I saw that parentheses. So let's simplify it a little bit before we go back and plug it in. And so notice we can distribute that 3 inside the parentheses. So that would give us 3x plus 3h plus 4. So none of those are like terms, and so we're going to put it like that. And now let's look at negative f of x. Well, to get negative f of x, basically we'd have to multiply both sides of this equation, f of x, by -1. And so we have negative of the whole quantity, 3x plus 4. So let's distribute that negative sign. And so we get negative 3x minus 4. Okay, so now we can put it all together. So it wanted us to find f of x plus h minus f of x all over h. So we have this piece here, this f of x plus h. We had found to be this 3x plus 3h plus 4. And then we saw that this minus f of x was this negative, oops, minus 3x minus 4. And put it all over h. So let's just simplify. So now I notice I have like terms. Notice we have a positive 3x in the numerator and a negative 3x in the numerator. Those go away. I have a positive 4 in the numerator and a minus 4 in the numerator. Those go away. So all we're left with is 3h in the numerator all over h in the denominator. And so a single term divided by a single term, we have like factors of h. So this is actually just equal to 3. So the difference quotient of f of x equals 3x plus 4 is equal to 3. So basically the difference quotient, I'm just going to kind of tell you, basically that difference quotient, if you're given an equation and you use that difference quotient, you can find the rate of change, how fast that slope is changing on that graph at a particular value. Well, if we go back and think about that equation that I just gave you, f of x equals 3x plus 4, that's a line. It's actually in slope-intercept form. I can tell my slope is 3. That graph, anywhere I chose a point on that graph, my slope is changing at a rate of 3 over 1, or is changing at a rate of 3. So pretty darn cool. So you can get into more than linear equations and be able to find the rate of change. What's happening on that graph? Is it going really fast? Is it steep? Is it growing? Are you making profit really fast? Or is it not a very steep increase? But if we're talking about profit, we still like to be increasing. Or is our profit decreasing? We don't like that. Anyways. One other thing, maybe I should go over one more of those at least. I'm going to go one more. The difference quotient. So I'm going to go harder. So let's find the difference quotient of h of x, which is 1 over x plus 3. Okay, so again, difference quotient, we're going to plug in x plus h, where Can we change that to G just because of the H and the H? I don't like it. So we're going to say this, recall this G of X. So difference quotient, G of X plus H minus G of X all over H. So we want to go in, we want to figure out what G of X plus H is. So you're going to go in, and wherever you see an X in your function G of X, we're going to put a parentheses, and then you're going to go back in and you're going to rewrite that. Put X plus H in the parentheses. So you have 1 all over, you see an X there, parentheses, plus, and parentheses, and then plus 3. So replace that. With X plus H. So really, when we simplify this, I can just drop my parentheses in the denominator, and I can't then do anything else. So 1 over the quantity X plus H plus 3. So my difference quotient, basically the minus G of X is just subtracting off that term G of X, which is 1 over X plus 3. And then put it all over H. So we have 1 all over X plus H plus 3 minus 1 over X plus 3 all over H. Okay, so we don't like things normally that are fractions within fractions, and so we want to rewrite it. So this is called a complex fraction because it looks complex. No, I don't know why it's called complex fraction, but because there's fractions within fractions by definition, and so we want to rewrite this. So there's a couple of different ways that you can simplify this. I prefer to multiply by the fancy one, my fancy one, and we kind of did this with solving equations to help us. Let's look at the LCD of those two fractions. And so our LCD, well, unfortunately, they don't have a common factor. Our LCD is the factor X plus H plus 3, all times X plus 3. Whatever we do to the numerator, we have to do to the denominator. So we just chose something so when we distribute it, those fractions would go away. So if I distribute that, the X plus H plus 3 cancels, and you're just left with a X plus 3. Minus, this is where I have to be careful. The X plus 3's cancel, but I have this negative outside. So that negative is going to have to go to this whole piece that's left, the X plus H plus 3. All over, and I'm not going to distribute my denominator, so I have an H times an X plus an H plus a 3, all times parentheses X plus 3. So we're almost there. We want to simplify. Let's distribute the negative. So X plus 3 minus X minus H minus 3 all over H all times X plus H plus 3 all times X plus 3. So again, things are going to start simplifying. In our numerator, we have like terms X minus X goes away. We have a 3 minus 3 goes away. So the only thing that's left in our numerator is this negative H all over H times X plus H plus 3 all times x plus 3. So I'm glad I didn't distribute because I might not have noticed, but notice now that we have an h in the numerator as a factor and an h in the denominator as a factor, strictly multiplication there. And so we can reduce, and we're left with -1, or you can leave the negative out front if you want, all over parentheses x plus h plus 3, all times x plus 3. Okay, so that's something we didn't really talk about or go over was complex fractions, but that also should be a review on how to simplify complex fractions. That's something that you'll see and you'll have to be working with these complex fractions a lot of times in calculus and be able to manipulate them to be able to get in the form you want. And I'm going to be referring to a lot now. This class, you might not see a lot of the benefit of knowing all this algebra now, but once you get into calculus, you'll see, oh, your life will be so much easier if you know all this stuff. If you are struggling with it and you here, then calculus is just going to be really hard. I'm not even quite done with this section. This section has a lot of information, and I kind of put a little bit of 3.2 in there. Let me pause. But I want to take a break before I go on. Okay, so we're looking at functions, and now we're going to look at operations of functions, things that you guys have done in the past, maybe just haven't noticed or have seen the notation for this. But basically, if you have two functions, f of x and g of x, and you wanted to add or subtract f of x and g of x, shorthand, you could write this as parentheses f plus or minus g parentheses x. So basically, it's just saying you're taking your equation, whatever f of x is, and adding it to g of x, whatever that is, or subtracting. I don't like in the way this notation kind of looks like you do the distributive property of x and you'd get this back, but that's not the case there. It doesn't mean the same thing. Here, if you were looking at multiplying your two equations, f of x times g of x, sometimes you denote that by the little dot in between. This is the same thing. You'll see it in this book written as f times g in parentheses, and then a parentheses x. And then division. If you had f of x over g of x, another way to write this is f divided by g in parentheses, and then parentheses x. If we were looking at the domain of these two functions, then we want to look at the domain of f of x and the domain of g of x, and we want to take what they share in common. Okay. One stipulation I have to put on the division, though, is that g of x cannot equal 0, which makes sense. We can't have any value, which gives us 0 in the domain. Okay, so the domain of the operation of the two functions is equal to the intersection of the set of the domain of f of x and the set, which is the domain of g of x. Okay, so we kind of talked about intersection was the upside down U. And when we were looking at two sets, and you're looking at the intersection, this is what they both share in common. So the elements that both sets share in common. Okay, so let's look at some examples. And it says for the given function, f and g, find the following for the parts a through d. Okay. So let's say, go harder. F of x is equal to the square root of x minus 1 and g of x is equal to the square root of 4 minus x. And we want to first find what is f minus g of x. So all this is saying is I'm taking my equation f of x and I'm subtracting off my equation g of x, which that's the square root of 4 minus x underneath the radical. It's not too bad, right? We got the square root of x minus 1 minus the square root of four minus x. So you just need to remember rules of radicals. In order to add or subtract radicals, they have to have the same exact thing underneath the radical, and they don't. And so we can't simplify this any further. So part B, let's say they wanted us to figure out what is the domain. So find the domain of f minus g of x. Well, we need to look at the domain of f of x. And we need to find the domain of g of x. And then we're going to look at what they both share in common. So the domain of f of x so trouble spot is any value which is going to give us negatives underneath the square root sign. And so x minus 1 cannot be negative. Another way kind of think the opposite. We know that x minus 1 has to be bigger than or equal to 0. And so those are not the values I'm going to exclude. Those are the values I need x to be in order for that to work. And so a linear inequality, we can isolate x, add 1 to both sides. We get x is greater than or equal to 1. So do the same thing. We want to find the domain now, but we want to find the domain of g of x. And g of x was the square root of, underneath the radical, 4 minus x. And so we're looking at when is 4 minus x greater than or equal to 0? We need a positive number or 0 underneath the radical for it to be a real number. So if we add x to both sides, 4 is greater than or equal to x. I'm going to rewrite this so that x is on the left. I just need to be careful with the way my inequality is facing. And so I have x is less than or equal to 4. So I have two things that need to happen. I have x has to be greater than or equal to 1, and x has to be less than or equal to 4. And so if you look at the number line, if you can't see it, you can graph both sets. Last week we did it on both above and below. So we know x is greater than or equal to 1. And so it's at 1, a bracket, everything to the right of 1. X is less than or equal to 4. So locate 4 on the number line. It's a bracket because it includes, as the equal to part, everything to the left of it. And so if we're looking at what they share in common, it's where they overlap. So the numbers they share in common include 1 all the way up to and including 4. So our domain, if it asked in interval notation, we would write bracket 1 comma 4 bracket. Or if it wanted it in interval notation, we would write it as 1 less than or equal to x is less than or equal to 4. Okay, so what if it said find g divided by f of x? So this is g of x all over f of x. We have to put on the stipulation that f of x cannot equal 0. Okay, so our equation of f of x, that was the square root of x minus, oops, it's g of x on top. So g of x, which is a square root of 4 minus x, all over f of x, which is the square root of x minus 1. If it said find the domain, though, we already pretty much did all of our work above. There's only one thing that we have to worry about, and that's when our denominator is equal to 0. So if it said find the domain of g divided by f of x, well, the only thing we have to worry about is when is g of x equal to 0. Not g of x, I'm sorry, denominator, f of x equal to 0. So when is the square root of x minus 1 equal to 0? So we looked at solving radical equations last week. We can get rid of the radical. We already have it isolated. Square both sides of the equation. We get x minus 1 is equal to 0. Solve for the variable. It's linear, so isolate it. X is 1. We had to be careful when we rose both sides to an even power because we could get extraneous solutions. But if I plug in 1 into this equation, square root of x minus 1 equals 0, it's true. So, but this is a case where x cannot be 1. So for our domain, before, we could include 1, but now, in this case, we cannot include 1 because that sets our denominator equal to 0. So our domain is going to be all numbers between 1 and 4, not including 1, but we can include 4. So pretty much what we've been doing, we've been working with equations to look at the relation. We've been looking at operations of functions, looking at equations, but we should be able to find domain and ranges by looking at a graph. We should be able to look at a graph and tell if it's a function or not. And I had mentioned that earlier today about the vertical line test. So the next section is more dealing with looking at the graphs and being able to answer questions and doing things that we were doing, but with graphs and not equations. I'm just going to change the page. So graphs of functions. So let's say you're given a graph. Actually, I'm going to pause the video. Okay, so I just kind of wanted to pull up some graphs. And so let's look at some graphs and be able to, from there, answer questions. So for instance, looking at this number 1, you should be able to identify what the domain and the range is. The domain, remember, is all the values of x that is included on the graph, and the range are all the y values. And so if I'm looking at this and I'm looking at my x values, let's look at where it starts. And so if you look at this, because there's a solid circle here and there's not an arrow, this tells me that this graph is not going any further than where this point is. It's not extending to the left. And so the value of x that starts that point there is starting at 2. And it's included because there's a solid circle, and so we're going to have a bracket there. 2, comma, and then you're going to the last x value. So it's hitting all the x values in between here until we get to this open circle, this point, and that x value here is 3. And so the largest value that we can get, except for not including it, but very, very close. So we put a parentheses there. And so any x value you gave me between 2 and 3, we could find a point on this line. So if you said right here, I could go up here and there was an x value, gave me a y value. And so for range, we look at all the y values that is included on the graph. And so if we're looking at our graph, the smallest, always go from smallest to largest. So smallest y value is at this open circle, and that smallest y value is occurring here. It's not including it, so it's a parentheses, and that value was at 1, comma, and so the next value that we reach, we're hitting all the y values between 1, and then it's stopping to that y value, which is 3. And we're including it, and so we're going to put a bracket there. And so it's everything that is shaded in between here. And though now asking, is it a function? Well, for every value of x, that's in our domain, does it correspond only to one y value? And we can look at that by that vertical line test. So if I drew a vertical line anywhere on the line between x equals 2 and x equals 3, I would see that it only intersects that graph once. And so that means it's a function. So yes. Okay, so now looking at the next graph, looking at the domain. So again, domain are all the x values that you're including in the graph. And so looking at this, I would look at the smallest x value. There's no arrows again, so I know that this graph is not continuing past these values. And so my smallest x value occurs here, but I'm not including that value because it's an open circle. I'm including any, because it's continuous between this, I'm including all values of x until I get to here. That's the largest x value, and we're not including it, so it's a parentheses. And so we could write that in interval notation from -4, comma to 3, and those are both parentheses because we didn't include the n values of that graph. And the y values, so go to the smallest y value on the graph this hits. Well, to me it looks like it's -2, but it's not including again because open circle. And then the largest y value was at +4, not including because it's an open circle. So it's everything that's in between here. So all the y values you hit on this graph are between -2 and 4, not including, so you put the parentheses. And it does pass the vertical line test. And so this is a function. So the domain for number 5. So looking at that, what are all the x values that are being hit on number 5? Think about it, see if you can look at that and see if you can determine domain, range, and if it's a function. So I'm going to pause the video while you guys try. Okay, so you guys just had a chance to look at this and try it, and I got some feedback that you guys, or some of you guys, or most of you hopefully are understanding this. And so domain are the x values. I always look at the graph and I look at my x, which is the horizontal axis, and I look at, does this graph extend on forever, or is there like a point or a solid open point? Where there's an open point, so that tells me that my x value here, the smallest value that I'm getting or getting close to is -5. Not included because of the open circle, comma, and then the largest value is 3. It is actually hitting 3. That's a point on the circle, and so I include that value. But when I'm looking at my y values, when I look at the smallest value on the graph, the smallest y value, getting very, very close, is -2. So a parentheses, -2. And the largest y value, getting close, not including, is +4. And then you mentioned that this was not a function, and you mentioned it was because it doesn't pass the vertical line test. So if we could just draw any vertical line on here and show that it's intersecting more than once. So here's one case. So since it's intersecting more than once, this is not a function. Okay, so if you've looked at the following, let's say we wanted to ask more questions other than domain, range, and is it a function? Let's say this is given to be f of x. And it wanted you to find f of -1. So you have to understand what that is representing on the graph. So what is that saying? What is it asking you to find? So what is that -1 representing? So this is representing the x value. So it's asking when x equals -1. This f of -1 is another way to represent your y value. So when x is -1, what is y? So when x is -1, go down, see what the point is on the graph. Your y value in this case is -3. If it said find f of -4, so when x is -4, this is representing your x value, what is y? So if we go over here, when x is -4, the y value we get is 0. If it says find x such that f of x is equal to -1. So this time it's asking us to figure out what the x value of our point is, and it's giving us the y value of the point on the graph. So it's telling us when y, what value of x? Gives us y equals -1. So if we go on to the graph and we look at -1, so look at y equals -1. So sometimes more than one x value will give us this, but if we look at it, when y is -1, if I do a horizontal line through that, so the point would be here. And so look at the x value that gives us that point when y is -1. So it's when x is equal to -3. So looking at a graph, you should be able to find when a graph is increasing, where it's increasing, decreasing, and constant. So be able to look at a graph and determine, you should be able to determine the following. Does that graph represent a function? What's the domain? What's the range of that graph? Where is the graph increasing? decreasing. And constant. Find local, we'll talk about it in a minute, maximum, minimum points. Find a y value given x. Find the value or values of x that give you y. Okay, so we'll be able to do that by looking at graphs of functions. Unfortunately, not all of this we can do by looking at an equation of a function until you have some calculus behind you. But that is one thing that you'll learn in calculus, and that will help you graph functions if you can tell where a graph is increasing, decreasing, where max and mins are. So let's say you're given the following graph. And you have a solid circle and x is -3, 0. We have a point at 0, 2. We have a point at 2, 0. And a point at 3, 1. Another thing that you should be able to look at or find looking at the graph are your intercepts. And then one other thing that we talked about last week was symmetry. Is it symmetrical across something? The x-axis, the y-axis, the origin? Okay, so looking at this picture, find the domain and range. So domain are all the x values. Because this is a solid circle at -3, 0, and the graph does not extend to the left of x equals -3, that tells me my graph, the domain is starting when x is -3. So the domain, putting it in interval notation, is -3, comma. I notice though that there's a arrow here. And so that tells me that graph is extending in that direction forever. So as it's going up forever like this, our x values are increasing forever. And so I notice that x values go into infinity. And so I have -3 to infinity is an interval for my domain. And my range though, So the y values that you guys are hitting, the smallest y value we hit is actually on the x-axis. So that y value is at 0. And because I had a solid circle here, and there's a point here, I know that 0 is part of my y value, my output. And then x values or y values I'm going to get back. Well, this is going on forever upwards, so I'm going to positive infinity. So part B, where are the intercepts? So look at where is it crossing or touching the x-axis. So the x-intercepts, well, notice there's actually 2 places. We have a solid circle here at -3, 0. So -3, 0. And it's dipping down, touching, but not crossing when x is 2, y is 0. My y-intercepts, there's only 1. It's right here. And this is when x is 0, y is 2. So it's at the point 0, 2. Any symmetry with respect to x, y-axis, or origin. Well, if we folded our paper along that y-axis, would you get a mirror image across that? The answer is no. If I folded my paper across that x-axis, well, in quadrant 3 and 4, there's no picture of my graph. It doesn't even dip down there. So x-axis, no. Origin, if I folded that in 4th, no. So what about decreasing? So we say a graph is decreasing on some interval. Well, looking at it, your graph is going down from left to right. So the graph goes down. From left to right. So we're kind of reading across left to right on the graph. Look at where, if you were walking on that, and if you were going to be going up or downhill, going from left to right, well, first you'd be going uphill, and then when you hit x equals 0, that's where your piece is going to start decreasing. And so we're decreasing here until we hit this x value. So you're going to you list the x value, it starts, to the x value it ends. Decreasing. So if I look at the x value it starts, I'm going to say 0. And the x value, it stops going down, is when x is 2. So you've got to be careful between interval notation and points. And when you're talking about interval notation and when you're talking about points. These are your x values. This is an interval. You're saying, and this is saying you're looking at all x values that fall in between, but not including 0 and 2. So if I'm looking at where is it decreasing, sorry, I just did decreasing, where is it increasing? So if we're looking at where is it increasing, I'm looking at where is it going up if I'm moving from left to right. So where the graph goes up. From left to right. So we go back over here and we're starting to go up. Well, at our x value we start at, we're starting to go up. And then we start to go downhill, and then we start to go back uphill when x is 2. So the x value that I start with, and we're always going from left to right, the x value that I'm starting with, and this is a solid circle. Because this is a point where I'm starting and it's not changing direction from increasing, decreasing, I would probably put a bracket there. So -3, we're going uphill. We stop when x is 0, parentheses, union, and then we start again when x is 2, and then we go increase until we go to infinity. Constant, a graph is constant. It's not going up or down, it's a horizontal line. And so if I look at this graph is never constantly going. There's never a horizontal piece in here. If I'm looking for absolute max or absolute minimums, I'm looking at, is there a peak or a valley? Is there a place where that graph is going to stop increasing and then start increasing? Or is there a place where that graph stops decreasing and then start increasing? And so those points are called local max and local mins. And so notice right here, we have 2 of them that are least obvious, right here and right here. So this is a max, it's a local max. And this right here is a local min, or minimum. If your graph stops and doesn't continue on, we can say that this point, which it does on this side, is also a local min. So when they ask if there's a local max or a local min, the local max and the local min are the y values, and the x values is where it occurs at. So if they ask for a local max or local min, so if they say where or what is the local max and local min? So if I said, what is the local maximum? This is the y value. So the y value that this is occurring at is when y is 2. So local maximum is 2, but it occurs And this is where we tell what x value. So it occurs when or at x equals 0. So the local min value is, so the y value, the smallest y value here, well, that y value, it's on the x-axis, is 0. So the local minimum value is 0. And it actually occurs at two values. It occurs when x equals -3 and x equals 2. So I saw one other problem here that looked kind of cool. So I wanted to do that real quick. So again, looking at a graph, actually, maybe before I do that, I probably should kind of just give you the formal definition. It's in here. It's not. That might be the next section. Increasing and decreasing, it is. Okay, so let's look at the following. So let's say you're given two functions, the graphs of two functions on the same axes. So let's say you have a parabola. The parabola, let's say, is intersecting at the x-axis at 2, 0. It has a vertex, so the minimum point is at 4, -3. Turns back around, hits the x-axis at 6, 0. It goes on forever. Yeah. And this is f of x. I kind of want to put a couple more things on here. Actually, this is g of x. Okay, let's do the other graph, the graph of f of x. And that's just a line. And you have a point at 2, 2. You have a point at 4, 1. Oops, that's not 2, 2. And you have a point at 6, 0. So if it asked you to find the following, g minus f, and then parentheses 6. So another way to write this is saying we want to look at what is g of 6 minus f of 6. So I need to go to my equation g of x. So when x equals 6 here, what is your y value? When x is 6 here, my y value is 0. So this is actually equal to 0 minus, and then f of 6. So minus, so when x equals 6, this is saying, well, also y is 0. So g of 6 minus f of 6, or g minus f of 6, is equal to 0. So if it said find g over f of 4, this is saying you want to look at what is g of 4 all over what is f of 4. So g of 4, so looking at when x is 4, g of 4, which is the blue one, that's -3. But when x is 4, so that's all over, for f of x, which is the pink one, or purple, that's 1. So we get -3 over 1, which is equal to -3. Okay, so that's a good spot to stop for today. And so we pretty much, let's